So good afternoon, everyone. Thanks to the organizer to give me this opportunity to speak. I have to say I'm very honored to speak at such a conference. I was, together with Michel Fruchard, I was the last PhD student of Krzysztof. And obviously, he taught me a lot, from most technical aspects to the ability to stay open to any topics of physics and mathematics. And also, after my PhD, I changed topic, and he was really happy for me and extremely supporting in helping me finding a job. So for all that, I would be eternally grateful. And I have decided to use this opportunity to speak, to present some work we did at the end of my PhD thesis about topological indices and topological insulators. So the guideline of my talk would be what I've called Gawedzky's relation for topological insulator, okay? It's probably not as universal as Euler identity, but I think it's really beautiful and it's short, and you can probably all remember it. Of course, everything is hidden in the notation, right? But still, I think it is a beautiful relation, and it's also a bit underrated to my opinion. So let me try to explain that to you. Okay, so what are these objects? So on the left-hand side, you have -1 to the k-milli of P, where that's the k-milli index for two-dimensional topological insulators with fermionic time reversal symmetry, and P is the Fermi projection. Of course, you're not familiar with all that. I will explain it later. And on the right-hand side, you have something that was mentioned already in several talks before. You have something coming from conformal field theory, the Wess-Zumino action. Okay, and U here is a unitary field on a two-dimensional torus. Okay, and I think it's a very nice connection between two distinct topics from topological insulator and conformal field theory, and I would like to explain it to you with a bit of details. But actually, the way it was discovered comes from a slightly different context, which is the one of a periodically driven system that we were working on in 2015 at the end of my PhD, and it involves several people. And this is what I would like to tell you first. Okay, so we worked all together at the time with David Carpentier, Pierre Delplace, who is also in the audience, Michel Fruchard was also a PhD student of David and Krzysztof, and myself. So this identity is simple, but there are a lot of mathematics involved. So this would be rather technical, so please try to stay with me. I've tried to put also some nice physics picture to have some breaks in between. Okay, so let me give you a very brief context of what is the physics of the problem for people who are not specialists. So we'll start with quantum Hall effect. You have a two-dimensional electron gas in a transverse magnetic field, and you're interested in the transverse conductivity. Right? Okay, so you measure the current with respect to some perpendicular electric field, and at low temperature, where you have all the quantum effects, you can measure the conductivity and see that it is proportional to an integer in a universal way and with extreme stability. I mean, meaning this is robust to many perturbations like disorder, defects, and so on. Okay, and here is a cartoon of the experimental curve with the celebrated plateaus of the Hall effect, and this is a test for the remarkable stability. And mathematically speaking, people were really excited about that, and there are many ways to define a topological index associated to this transverse conductivity, from fiber bundle theory, gauge invariance, non-commutative geometry, Fredholm theory, probably many others, and it's still an active topic, both in mathematics and physics. Okay, so that's the initial motivation. And a sub-branch of this field would be what are called topological insulators. So here we consider independent electrons on a lattice, okay? So for example, Z2, my talk would be mostly two-dimensional, and you have some dynamics for the electrons, think about Laplacian plus potential, and you will have a topological insulator if, depending on the spectral properties of your Hamiltonian, for example, existence of a spectral gap, you can define a topological index, namely associate to your Hamiltonian an integer into a continuous way, so that this function is locally constant. Okay, and you will speak about a topological insulator in that case. Then you have two pictures. That would be the bulk picture. The system is infinitely extended. And you also have the edge picture, where you cut the system. You take only half infinite space, truncate your operator, and you will see appearing these so-called chiral edge modes, which are confined near the boundary of the sample and propagate only in one direction. And they were mentioned by David Carpentier right before. And there is also a way to count these edge modes and define a topological index. And the two are related by the so-called bulk edge correspondence. Okay, so this is the general setting. You take some lattice, you take some dynamics, and you try to define topological index and show that they are stable and show that there are edge modes and so on. Okay? So that's the general playground. And now you can add more symmetries, you can change the dimension, you can put some more physical ingredients and try to define topological indices. Okay, and that's what we are going to do next. Okay, so that was the general context, and now I would like to speak first about some index for periodically driven system. And it turns out that the relation I've shown at the beginning is, in a sense, a consequence of this previous work. So I would like to tell you first about periodically driven system, then go back to Gavinskys' relation, and if I have time, speak about some recent developments that were consequences of all this work. Okay, so let's start with periodically driven systems. So again, we are in the context of topological insulator, so I'm interested in independent electrons on a two-dimensional lattice. So you have a Hilbert space, and the system is ruled by some Hamiltonian, which is time-dependent in a periodic way. Okay, so it's time-dependent, and you have a period t. So you can think about some material, and you add some periodic driving. For example, you send some light on the material, and you hope that some new topological properties occurs in presence of the driving. Another way to see that these systems are interesting from the topological point of view is to look at this toy model by Rudner and collaborators, where the Hamiltonian is time-dependent but piecewise constant. Okay, so you have 4 steps, and for each step, 1, 2, 3, 4, you open the bounds where the electrons can jump. Okay, so here on the red bound, then on the blue one, then on the green one, then on the yellow one, and so on. Okay, so you have a periodic driving, which is very artificial, but it is really an archetypic model of these driven systems. If you look at the dynamics in the bulk, well, you will see that the electrons are trapped around orbits, a bit like in quantum Hall effect. I mean, the model is designed for that. And if you look at the boundary, you will see that the electrons can flow only in one direction, and you kind of reproduce these chiral edge modes. So there is a good chance for topological properties in these driven systems. And the mathematical question is, what is the topological index of this problem? So what's the starting point? You have the Hamiltonian, and we will assume that the system is translation invariant, meaning that the dynamics here is the same as here. Then there is something very well known, is Bloch decomposition or Fourier transform, depending on where you come from. And you end up with a family of matrices, depending on time in a periodic way, and momentum living on the two-dimensional torus because you start from the two-dimensional lattice, right? So that would be the starting point. I give you a model which is time-dependent and which is parameterized by this K momentum on the two-dimensional torus, and I work with self-adjoint matrices. Okay? And the question is, what is the topological index for this problem? Okay, so now we need to work a bit to construct the index, and here is the construction. So first of all, when the dynamics is time-dependent, it is more interesting to look at the spectral properties of the unitary propagator, which is generated by Schrödinger evolution. Okay, so here it is. And the propagator starts at 1, and then it's generated by the Hamiltonian. And even if the Hamiltonian is periodic, then the unitary evolution is not, but it has these nice properties, which means that if you know the evolution after one cycle, this U of capital T is called the Floquet operator, and the dynamics along the first period, then you know all the dynamics. Okay? There is the stroboscopic motion and the micromotion. In general, the Floquet operator is not 1, unless you tune precisely your model. And the main assumption in this topic is to have a spectral gap for this unitary family. So for each k, this is a unitary matrix, so the spectrum is on the circle, and you collect all the eigenvalues, and this gives you the spectrum of the operator, and you assume that there is a spectral gap in this problem, okay? And the model I've shown before satisfies this assumption. So that's a bit artificial, but it's, let's say, to build a time periodic evolution. So U is not periodic, but we will build a unitary map which is periodic in time. How to do that? Well, we take a logarithm. We define the effective Hamiltonian, which is the logarithm of this operator, and we use the spectral gap assumption by taking the cut inside the gap so that everything is well defined. In particular, if you exponentiate the logarithm, you recover the Floquet operator. Now, you can define the effective evolution where you multiply your physical evolution by this exponentiation of effective Hamiltonian. And just by construction, this is a map which is periodic in time, okay? So you end up with a family which is periodic both in time and in Bloch momentum, okay? So you have a family from the three-dimensional torus into the unitary matrices. Now, for such a family, there is an index, which is called the three-dimensional winding number, and it goes as follows. You have your map, and you have integration over the three torus, and then you have, so time and Bloch momentum. And you have it involves the derivatives in time and in Bloch momentum, okay? So this formula might be a bit heavy. So if you come from differential geometry, there is a more compact way to write it with v minus 1 dv to the power of 3. And if you are not familiar at all with this problem, then just think about some winding number. You have a function onto the circle which is periodic, and you are just counting how much it is winding around the circle. So that would be a three-dimensional analog for such index, okay? And this is a mathematical index, but it has physical consequences in the sense that in each gap of the Floquet operator, so that's the spectrum of the Floquet operator, so this is periodic along the vertical direction. Then as long as the index is non-zero, then you see chiral edge modes appearing at the boundary of the sample, according to the bulk edge correspondence, okay? So that's what the state of the art when we started working on this project. And the question was, what happens to time reversal symmetric systems, okay? We know from static topological insulators that something should happen, and actually something happens, and there will be a need for a new index. And this is what we did. Okay, so we have a 3D index, and now we would like to implement time reversal symmetric models. So for electrons, time reversal symmetry is implemented by an anti-unitary operator theta, which squares to -1, and which has the following properties on your family of matrices. Okay, it's commute up to the price that you flip time and Bloch momentum. Okay. Now you have the same assumption on spectral gap. You build the effective Hamiltonian. You build the effective evolution, and you realize that the effective evolution satisfies the same relation, except it's a unitary operator, okay? And as a consequence, if you compute the integral for the index, it's always 0, okay? Actually, you can see from this relation that if you know the dynamics from the first half of the period, then you know it by time reversal symmetry on the second half. So there is some redundancy into the evolution, and the index is just 0 because the two terms compensate. So we need to build a new index for this story, okay? So since all the information is known for the first half of the period, we can forget about the second and try to extract some physical information from this first half. Now, notice that at the fixed point, t over 2, then we have the following relation, which I would call static time reversal symmetry, because time is not flipped, okay? It's only momentum. And the idea to construct the index is to deform this object to 1 by preserving this static time reversal symmetry. So let me say it once again. This is the original evolution. So this is t, and this is momentum. T and minus t are related. The information here is redundant, so we just forget it. And we will build a new evolution which keeps the first half unchanged, and then contracts the evolution to 1 by preserving time reversal symmetry at each time, if you like. And that's the work we did in 2015. We showed as a mathematical theorem that there exists a deformation, V epsilon tilde of V epsilon, such that you start and you end up at 1. For the first half of the period, that's your original physical evolution. And for the second half of the period, you have this fixed time reversal symmetry, okay? So this is a new evolution, which is periodic in time, so you can compute the three-dimensional winding number. But of course, I mean, it's not enough to show that there exists some deformation, but there might be several. So what happens if you have two such deformations? Then what we show also is that if you take two such deformations and compute the difference of indices of 3D winding number, it's not 0, but it's an even integer, always. And so you can define the topological index k of V epsilon as the three-dimensional winding number of any of such deformation, but modulo 2. And that's our Z2 index. Either it is topologically trivial, 0, then the system has no edge mode, or it is 1, non-trivial, and you will have edge modes, okay? All right, so a bit of physics. There is some relevant model to look at the edge modes and the topology of this problem. So it's basically two copies of the previous time model I've shown. So you take into account spins, and spin up are going that way, and spin down are going the other way around. So let's say spin up are going to the red path, and the blue ones is for the spin down. And of course, you can couple the spin a bit to perturb the system so that it's just not two trivial copies of the same system, okay? And then you can compute the index and look at the Floquet spectrum in presence of a boundary, and you will see that when k is 0, you have no edge modes, and when k is 1, you have edge modes, okay? And so this index characterizes time reversal symmetric periodically driven systems. Okay, so I have no time to speak about the proof, but it's basically deformation of matrices. We have family of matrices living onto the three-dimensional torus, and the only thing you can remember is that the fixed point of the time reversal symmetric operator is the compact symplectic group, which is connected and simply connected. Okay, so you can deform your unitary map to 1, starting from the most symmetric point of the brilliant torus, and then extending it and showing that there are no obstructions. Okay, I will not speak more about that because I think it's too much. Okay, so this is a lot of mathematics, so let's speak about some physical applications of this problem. So the question was raised before. In Floquet systems, topological insulators consider that the electrons are independent, no interactions. But in Floquet systems, if you tune the interactions on, then the system will heat up, and there's probably no chance to see that in electronic systems. However, you can see these Floquet topological properties into classical systems of optical waveguides with evanescent couplings. So let's consider first a one-dimensional model here, where lights propagate along the z directions, which play the role of time, right? In German, z is for Zeit, so, okay. You have this chain of light propagating, and when the wires are close enough together, the light can flow a bit by evanescent coupling into the next one. And this is the same as hopping for electrons, okay? And you can reproduce, and formally the equation is the same as Schrödinger equation for light, up to some approximation, and you can see the appearance of edge modes, okay? And this is from a group in Nice, but Pierre Delplace did part of the theoretical work for that. And there is a two-dimensional analog of that, including with fermionic time reversal symmetry, where they see these chiral edge modes in the group of Alexander Zeimreit in Greifswald, okay? There is also a connection with quantum works, but I don't have much time to speak about it. Anyway, all these systems have topological properties, chiral edge modes, which are captured by these Floquet topological indices. Okay, so that was the first part, so some independent story. And now I would like to go back to Gawedzky's relation and speak a bit about Wess-Zumino amplitudes. So how it is connected to all that. So first, remember there were two parts, Kane-Mill invariant, Wess-Zumino amplitudes. And I need to speak a bit about Kane-Mill invariant because, well, it's part of the formula, but I won't insist too much on it because by lack of time, and also because there are already too much indices that have been defined. Anyway, let me present it briefly. So forget about periodically driven systems for a while. So we are dealing with a static system, time-independent, still time-reversal symmetric on a 2D lattice. So you have a family of Hamiltonians, which are time-reversal symmetric. And so it's a static problem. You consider the ground state of the system, and you assume that the Hamiltonian has a spectral gap, and consider the Fermi projection. So collect all the eigenvalues below some Fermi level in the gap. That's the Fermi projection, and that's the essential object of the theory. Okay, and K is still along the two-dimensional torus, Bloch momentum for two-dimensional lattices. So there is an example of the model, Kane-Milli model, where you have electrons hopping on a honeycomb lattice with spin-orbit coupling. I'm not going to detail that, but it has a spectral gap and it has non-trivial topological properties. Okay, just if you're curious, such model exists and spin is not conserved. Okay, so now the Kane-Milli invariant. So I put this slide just because some people like to have formulas, but I won't insist too much on that. So basically, you start from the Fermi projection. There is a way to build a matrix from it with some global eigenbasis for the Fermi projection. And the two-dimensional torus can be seen as a square with periodicity. On this torus, the time reversal invariance maps k to minus k. So up to periodicity, there are 4 fixed points for this involution, 0, 0, 0 pi, pi 0, and pi pi. Okay? And for each of these points, you can compute the Pfaffian of this antisymmetric matrix with respect to the square root of this determinant. Okay? So it's a messy formula. I mean, it's really a Z2 index, but I cannot spend too much time on it. Okay? But it exists, and it defines a Z2 index for these two-dimensional static systems with fermionic time reversal symmetry. And you see, what is a bit disappointing here is that it's not very geometric, or you don't really understand the origin of this formula, which is localized at 4 points only. So it attracted a lot of interest in the mathematical community, and people were really looking to have some geometric interpretation of this formula. And this is where we can use our previous result. Okay? Okay, so what is the relation between static and periodically driven system? Well, we just pretend that our static system is time-dependent in a trivial way. So you start with the Fermi projection P here, and you consider the following time evolution, e to the 2 pi it p of k. Just by construction, this is a periodic map that starts and ends at 1, and it is time reversal symmetric when p is. Okay, so it flips time and k. So remember that the spectral gap assumption was used to build a periodic map in time. But this is already periodic. So there is not even a need for a spectral gap assumption, no need for effective Hamiltonian effective evolution. We just have a periodic map. And at the half period, the fixed point of time reversal, just by a simple computation, the unitary is just 1 minus 2p of k, and that's called sometimes the Fermi unitary. Okay, it's a unitary, right? It's quite common, and it was appearing in the formula at the beginning. Okay, so this is a periodic evolution, which is time reversal symmetric. So we can apply our Z2 index. So let U tilde be a deformation of U such that our index, remember it's a 3D winding number modulo 2, is well defined. We have shown that this always exists, and it's, right, well, that the index is well defined modulo 2. So we can compute the index, okay, and realize that the first half of the time vanishes, okay, just because this evolution is extremely simple. So if you like, the t and k variable are separated, and the computations leads to 0. So we are left with the following expressions, which is integral for the second half of the time over the two-dimensional torus of this trace of u minus 1 du to the 3. And if you are familiar with Wess-Zumino amplitudes, then this should ring a bell now. Okay? So let me just comment on it. So we have u tilde starting at up of k at t equals 1/2, At t equals 1, it's 1. And all along, you have this static time reversal symmetry. So we'd say that U tilde is a time reversal symmetric contraction of UP to 1. OK? So because we are not all familiar with Wess-Zumino amplitude, I would like to define them connected with this formula and mention the contribution from Krzysztof to these aspects of conformal field theory. OK, so let me give you a general definition of Wess-Zumino amplitudes and then come back to our problem. So take sigma a closed-oriented surface, like the two-dimensional torus, and G a compact Lie group, and phi a field from the worldsheet sigma to the target space G. Then consider some extension, sigma tilde, a 3D manifold, which has the boundary sigma, okay? And consider a field which extends our previous field to this to a field from sigma tilde to G, okay, an extension. Now, the Wess-Zumino amplitude is defined as follows. It is the integral over sigma tilde of phi minus 1 d phi to the 3, okay? That's the Wess-Zumino action, sorry. And of course, if such extension exists, it might not be unique for similar reasons. And if you compute the Wess-Zumino action for two different extensions, you realize it is 2 pi z valued. So that the Feynman amplitude, or the Wess-Zumino amplitude, is well-defined, which is what matters in the quantum field theory. Okay? So this object is well-defined. And this is really a central concept of conformal field theory and Wess-Zumino Witten. They were mentioned several times, and there could be plenty of talks on it. I mean, this is related to string theory, to many things. And here, I'm not going further, but I just want to connect it with our problem. So in our case, the torus, the sigma, the manifold, the worldsheet would be T2. The Lie group would be UN. And the field would just be UP, 1 minus 2p on the two torus. And if you compare the two expressions here and here, well, just up to a coefficient, our index is the Wess-Zumino action divided by 2 pi modulo 2. And what our theorem shows is that if you consider only time reversal symmetric extensions of U to define this action, then they are actually 4 pi z valued, I mean, the difference between two contractions. So that you can take the square root of it, of the amplitude, or 1/2 of the action, if you like. And you end up with the property that -1 of this periodically driven index is the square root of the Wess-Zumino amplitude of UP, okay? But that's not the end of our story, sadly, because this is not Kane-Milli. This is K of U. This is an index for periodically driven system. So now the question is, how do you connect this index with the Kane-Milli invariant? And that's actually where the technology of Wess-Zumino amplitudes enters in the game, because we'll actually compute this explicitly to end up with the Kane-Milli invariant. Okay, and this is the last part of the story. Okay, so now I would like to spend some time on what Krzysztof did to define the Wess-Zumino amplitude, because I think this is an essential part of his work, and I think he always liked to come back to this formulation, and I remember having a lot of discussion on it at the time I was doing my PhD. So here is the local approach for Wess-Zumino amplitude, which would be very helpful to compute our index. So imagine, so the Wess-Zumino amplitude are defined here, where chi is this tree form. Imagine that you are lucky and this tree form is exact. So it's the derivative of some 2 form, okay? Then by Stokes' theorem, this is just the integral over sigma of this 2 form B. And here the extension completely vanishes, and you don't need it. But of course, this is not always true that chi is exact. But what you can do is cover your manifold into small open subsets where the tree form is always exact. Okay? So take a good open cover, meaning that all open subsets are contractible and also there are intersections. And on each open subset, this tree form is exact, so you can write it as a dBi. But then if you look at the intersection of 2 subsets, you have Bi and Bj, and they coincide up to a 1 form. This gives you a 1 form on 2 intersections, and then you can go down. This gives you a 0 form or a function onto 3 triple intersections, and then you have this cocycle condition to make everything consistent. Okay? And there's some freedom in this construction in the choice of forms and open, but there is some way to define equivalence classes of it, which I will not do, but for those who know, this is giving the Deligne cohomology class of degree 3, which involves a cohomology of sheaves and cohomology of forms, okay? And so this local data gives you a well-defined object that you can use to compute Wess-Zumino amplitudes. What you do is you triangulate your worldsheet sigma so that it's into cells, edges, and vertices, so that each part is sufficiently small to be sent in one of these open subsets, and on where the tree form is exact. Okay, and now you see you define the Wess-Zumino amplitude as the sum over all cells. On each cell, the tree form is exact, so you have this formula which is the same as here. But of course, you have to glue all the pieces together so that the expression is consistent. So here is the remaining part of the formula. And you can show that this is completely independent from all choices of the construction, meaning choice of open subsets, choice of forms, choice of triangulations, and so on. And it coincides with this original definition of extension. And Krzysztof did this in 88, and I think it is really fundamental in all his research. Okay, this picture is taken from Krzysztof's paper, and I think every paper on conformal field theory has the same figure of triangulation. Okay, so you can use this local data to actually compute Wess-Zumino amplitudes in a very explicit way. And there is also a cherry on the cake, if you like, that there is a geometric interpretation of this local data approach, which I won't describe in detail, but just mention. And these are the so-called bundle gerbs, or more precisely, Hermitian line bundle gerbs with connections of curvature chi, okay? And you can show that this local data have a geometric interpretation where the Wess-Zumino amplitudes are, in a sense, the holonomy of the phi over the gerb G, okay? And this is really analog to parallel transport along passes, except that here your field is living on the surface. So it's really parallel transport along some surface. And this allows to generalize Wess-Zumino amplitudes, in particular to worldsheet with boundaries, which is not possible with the original definition. Okay, and there has been a lot of work on that in boundary conformal field theory in particular. And these gerbs, characterizing the local data, were constructed over all compact and connected simple Lie groups, like SUN, because, I mean, if you look at the classification of Lie groups, this is a very natural thing to look at. But in our case, we are working with the unitary group, which is not simple, but it's the natural gauge group of non-relativistic quantum mechanics, okay? So somehow the gerbs were not constructed over it, but Krzysztof did it, and if you look at the proof, the construction of the gerb over this group is really inspired by the theory of Floquet topological systems, okay? And on top of that, you can implement time reversal symmetry through an equivalent structure over the gerb so that the square root of the holonomy, or the square root of the Wess-Zumino amplitude, is well defined, okay? And this is not only a beautiful geometric construction, it is also very explicit and very helpful to compute amplitudes for specific fields. And this is what we did to end up with the Kane-Milly invariant, namely the Pfaffian formula localized at the 4 points, okay? So in our first work altogether, we used the gerb over SUN and circumvented somehow the problem of UN and take some very long path coming from periodically driven systems. But then I went away and moved to a different topic, but Krzysztof realized that this relation is actually independent from topological periodically driven systems, and rewrote the entire proof with the gerb and the equivalent structure over the unitary group, okay? And that's it. I think that's a very nice relation. I think it's a bit underrated, to my opinion. You can have a look at this paper from Krzysztof from 2015. There are some lecture notes that he gave in Geneva. He was invited by Anton Alexev, I think. And they are really easy to read, and I really recommend it to people interested in that to read this work. And again, I mean, in a sense, this is independent from periodically driven systems, but in the proof and in the work, there is a lot of influence from this theory to actually compute these relations, which I call Gawedzki relations. So if you like this formulation, please share it. Okay. So I think this is the most significant contribution from Krzysztof in the field of topological insulators. Right, so in the remaining time, I would like to speak briefly about some further developments into the world of periodically driven systems that I did after my PhD. I moved to Zurich and worked with Jean-Michel Graf, who is also in the audience. And it's about the same story, but with disorder. So here, we would like to forget about translation invariance and also time reversal symmetry and work with operators rather than matrices. So the Hilbert space is infinite. That's just L2 of Z2 and internal degrees of freedom. You have a family of operators, which is time-dependent but periodic. And you replace translation invariance with a much more general assumption, which is short-range property, meaning that the off-diagonal matrix elements in space are exponentially decaying. So it's a very general assumption. Then there is still the gap assumption. So you can work with many assumptions. So you have the spectral gap that you can keep. It's not working very well. So you have the spectral gap, but you also have, for those who know, the mobility gap assumption, where the gap is filled by states which are localized in the sense of Anderson localization. And you can also consider this funny situation where the whole system is completely localized. So the Floquet operators, describing the dynamics at each time capital T, is completely frozen. But still, because of the micromotion in between, there might be some topological transport. Okay? And there is no analog of that in the static case. If the whole system is completely localized, then there are no edge modes. Okay, so that was one motivation. Anyway, you have this setting with a spectral gap or mobility gap, and you would like to define some index. So you can build the same objects, but in a different language, because now you are working with operators. So you have Hamiltonian, unitary evolutions, effective Hamiltonian, effective evolution, and you have to show that they are all short-range operators on your infinite Hilbert space. And now the formula of the index is very close to what I've shown you before, this three-dimensional winding number, except that you integrate over time, and integration over momentum, which is not there anymore, has been replaced by a trace over some infinite dimensional space, right? And the momentum derivatives have been replaced by some kind of non-commutative version of it, P1 V epsilon and P2 V epsilon, where P1 and P2 are half-space projections, so projecting onto the upper half space or on the right half space, okay? And of course, you have to work, you have to show that this formula is finite because not operators are trace class. You have to show that this is integer valued, that this is continuous, but you can do all that, and you can actually connect this object with a Fredholm index, for those who know. And there is also a very nice story because you can define an edge index, gives a physical interpretation, and show a bulk edge correspondence theorem for this problem, okay? And I was not working a lot on a periodically driven system for a while, but then I came back to this, actually thinking about preparing this talk. And this is just work in progress, but I have good hope it will work. So my idea is just to generalize what we did in the translation invariant case for the Z2 index to this disordered setting. So basically build the same contraction, but not for family of matrices, but for operators, okay? So I'll spare you the details, but basically, I would like to mimic this Z2 index into the language of operators. And if it works, as a byproduct, we will have some Wess-Zumino action or Wess-Zumino amplitude in a non-commutative or functional analysis framework. Okay, so I'm not sure it would be very useful, but it would be beautiful anyway. Okay, so I think my time is almost done, so I should conclude. So let me just conclude in one slide. So I wanted to tell you about this relation from topological insulator, which is short enough that you can all remember. And I think this really illustrates Krzysztof's impressive ability that he had to establish very surprising connection between very distant topics from both mathematics and physics. And this is probably just one example among many, probably you have in other fields of mathematics and physics. And I think we should all follow this path and stay very open and curious to many fields of mathematics and physics, because you never know, it may pop up somewhere later in your research. So thank you very much for your attention.
Thank you very much. Other questions?
So I have a question in connection with this beautiful formula relating Kane-Mealy and Wess-Zumino.
Mm-hmm.
So fermionic odd or fermionic time reversal symmetry is just one of many symmetries a topological system can have, including no symmetry. Right? And are there formulas for other cases too? In fact, in the case of no symmetry, I think you just in passing showed that there is one too.
Right.
But what about particle hole or other symmetries?
Right. So, well, you should look at the table in dimension 2. So I think this is the no symmetry case is here. Okay. So see, if you have no symmetry, that's the index. And now, if you look at other symmetry classes, you could probably do the same, looking at this index will probably be 0, and then you could try to build another deformation, and so on. Actually, I think there is a work which classifies all the Floquet index by just mapping them to classical static system, well, to static systems. Okay, so yeah, you could do it absolutely. I think you could look at the table where the index is non-zero, and in the static case, and try to build an analog of a Floquet index there. But I think it has not been done. Yeah.
Yeah, my question was on the fact that you have an invariant which is only defined modulo 2 or something like that. And my question is that how can this jump of 2 can appear? For example, if you have a path of Hamiltonian and you have, for example, an invariant which is equal to 1, and you say that it is only defined to modulo 2, so how can it happen that it jumps, for example, from 1 to 3 and things like that? Is it from the fact that your application, there's some point where you define an application on the other half? Is it the fact that this operation is not completely explicit?
If you are asking physically speaking, how can you jump from one edge mode to 3 edge mode, this I don't know, and this is completely underlooked in the literature. Like, people look only at one edge mode and are happy, and you never see a transition without closing the gap from 1 to 3 edge mode, and this is indeed an interesting question. From the mathematical point of view, you can just compute the difference of two indices and see explicitly that this defines a map which has an even index. Okay, it's just in the proof you can see it explicitly that this map has the symmetry required for the index to be even.
And then this map V tilde, is it fully explicit when you have a V, or is that some kind of abstract argument that says that you can show that it must exist, but you...
The price, I mean, it's not as explicit as you would expect, but it's only you need to know explicit paths in the compact symplectic group, and they are not all explicit, but for a specific model, you have good chances to know it explicitly, I think. Yeah.
I have, okay. You have this beautiful formula which connects the Kane-Mealy index to Wess-Zumino-Witten. Mm-hmm. Now, you gave a definition of this Wess-Zumino-Witten amplitude which was purely mathematical, but if I understand, it comes from conformal field theory, right?
Right.
So is there any way we can apply this physical content of conformal field theory via this formula to topological insulators?
No, because I think you see, this is coming from conformal field theory, but that's only the topological part of conformal field theory. So in our business of bulk topological insulator, there is no conformal invariance. Okay, so you cannot import all the technology from conformal field theory. If you look at edge modes, as David was saying, then you can import everything from conformal field theory for the dynamics of the edge modes. But for the bulk invariant, it's just a mathematical connection that you realize that these topological expressions appear.